Hello everyone, this is Chen. It's my pleasure to present our work, Calibrating Deep Neural Networks by Pairwise Constraints. This work was done by Chen and Luna Vasconcelos at UC San Diego. For many real-world tasks, such as weather forecasting and medical diagnosis, it's important that a classifier provides not only accurate predictions, but also accurate confidence estimates. Therefore, the problem of probability calibration has long been studied in machine learning community. In recent years, an emerging challenge is the calibration for deep neural networks, which tend to be overconfident in their predictions. A DNN estimates the class posterior probability by a nonlinear embedding and a softmax regression. A probabilistic classifier is perfectly calibrated if it can deliver the true posterior probability for any pair of observation and label. For example, given 100 predictions, each with posterior of 0.9, we can expect 90 of them to be correct. DNNs are typically trained by minimizing the cross-entropy loss. Note that the cross-entropy loss only provides explicit supervision to the posterior probability of the class to which the observation belongs, while some supervision is implicitly provided to the other classes, through the constraint that the posteriors must sum to 1. This implicit supervision is very diffuse. The problem is particularly acute when we have a large number of training classes. Inspired by the idea that a multi-class classification problem can be reduced to a set of 1 versus 1 binary problems, we propose a hypothesis that the calibration of a multi-class DNN can be strengthened by providing supervision to all binary problems derived from the multi-class problem. In this work, we show that this hypothesis has a strong theoretical motivation, in that the multi-class probability estimator is calibrated if and only if all the derived binary probability estimators are calibrated. In practice, we observed that the binary posterior estimators derived from a vanilla DNN are poorly calibrated in two aspects. First, when binary estimators that involve the true class make incorrect predictions, these predictions tend to be associated with high confidence. Second, for binary problems not involving the true class, the binary estimators mostly assign the examples to either of the two classes with high confidence, instead of producing uncertain predictions. In light of this, we propose two training constraints on the pairwise binary problems. We start by considering the problems involving the true class. To calibrate these problems, we resort to the binary cross-entropy loss. It remains to consider the binary problems that do not include the true class. For such problems, the observation does not belong to any of the two classes, and the true binary posterior is unknown. In the absence of more information, we chose to minimize the KL divergence between the binary posterior and a non-informative uniform prior. In practice, we observed that using such prior can effectively improve the calibration of deep neural networks. Finally, the two types of pairwise constraint are combined with the cross-entropy loss into an overall objective. We empirically evaluated our proposed calibration approach on Cypher 10 and Cypher 100 datasets with different network architectures. To start with, we evaluated the calibration error of DNNs trained with and without our constraints as a function of the number of classes. This was done by randomly sampling subsets of training classes from the dataset. It is shown that the calibration performance of vanilla DNNs degrades drastically with the increase of the number of classes. In contrast, calibration error for our approach was maintained at a relatively low level for different numbers of classes. Furthermore, our method was evaluated on the different levels of data shift. As compared to many popular single-model calibration techniques, our method was shown to achieve better calibration performance and comparable classification accuracy. In addition, we evaluated the compatibility of our method and the popular method of deep ensemble. It is shown that the deep ensemble can also benefit from our constraints. This is the end of the video. Please refer to our paper for more details of our work. Thanks for your watching.